Hello, we are introducing ourselves to a new topic, that is sulfur and its compounds. Like you can see, it is divided basically into two. We have sulfur and then we have the compounds of sulfur. But before I proceed, I would like to encourage you to observe the standard operating procedures during these COVID times, because it is real and it actually kills. So we shall begin by looking at sulfur. Sulfur is the second member of group 6 of the periodic table. And if you have a periodic table, you can see that it is just located below oxygen. Its atomic number is 16 and the mass number is 32. The atomic number being 16 means this electronic configuration can be written as 2 to 8 to 6. From that electronic configuration, you can be able to deduce its valency. So its valency is 2. But we have also been able to see that in some other compounds of sulfur, like we shall see later on, it can show a valence of 4 and then a valence of 6 towards oxygen mainly. It's a non-metal, like we saw in our opening slide. It's yellow in color. So the color for sulfur is basically yellow. So here we have some details to show us to show us more about what this sulfur is. It's yellow in color, like you can see on the right hand side of our slide, and then its atomic number is 16 and then the mass number is 32. And then we can also see that the electronic configuration, we have written it there, it is 2 to 8 to 6. If you look at group 6 of the periodic table, which we are calling group 16 in the modern periodic table, you can find it in group 6, which is just below, where it is just below oxygen. To proceed, occurrence, first of all, how can this sulfur be obtained, or how can it be found? It can be found in free form. It is a solid in nature, and it's found in the ground. In the world, many of the sulfur deposits are found in states like Texas and Louisiana. Then it can be found as the product of petroleum, for example, as hydrogen sulfide, and then it can also be found in a combined form as iron pyrites, or what we are calling lead sulfide, or what we call galena. On the right hand side, we are showing a picture which is showing us some of the mines of this sulfur. So basically, there are three ways in which sulfur can be found: either in free form. There are some parts in the world, especially in the United States, like I've said, and the Middle East countries like Pakistan and the like, where sulfur can be found. And then as petroleum gases like hydrogen sulfide, where we can be able to obtain it by what we call fractional distillation of petroleum, a process known as refining. And then it can also be found combined with metals, especially lead and iron. After knowing that, how can we obtain it from where it is found? The major process by which sulfur is obtained is what we call the Frassich process. This is named after a German scientist known as Hermann Frassich. What is actually done: a hole is dug about 30 centimeters in diameter into the soil, and then it is lined with an iron pipe to provide support. Then three iron pipes, three tubes are sunk into the ground. They are concentric, meaning that they have a common center. And then of the three tubes, like you have one tube inside another and then inside another, so there are three, one inside the other, like that, forming 3. And then what is actually done is, in the outer tube, superheated water at about a temperature of 170 degrees Celsius is forced down at a pressure of around 10 atmospheres. What will happen is, this water, once it goes where the sulfur is, what we are calling the sulfur beds or the sulfur deposits, it melts the sulfur. So what the sulfur will flow into what we are calling the reservoir. You're going to look at our setup in the next slide. And then hot air can be forced through the middle pipe into the sulfur beds, and then the sulfur will come out through the middle pipe. So here we have our illustration. We have superheated water at 170 degrees Celsius under pressure forced into the outer pipe. So it goes where the arrows are showing us where the sulfur is going, into the sulfur beds. It will melt the sulfur, then it goes into the kind of reservoir at the bottom of that apparatus or that setup of ours. Then if we force hot compressed air at a pressure of around 20 to 20 atmospheres through the middle pipe, the sulfur will be able to flow out through the outer pipe. The sulfur we collect here is about 99%. Then sulfur can also be obtained from natural gas, like I've said, and in this natural gas we have hydrogen sulfide. So the hydrogen sulfide is quite a lot, so we react it with oxygen to give us sulfur dioxide and water. But because the hydrogen sulfide is a lot, some of the hydrogen sulfide remains unreacted. So what we'll do is the hydrogen sulfide which has remained unreacted reacts with the sulfur dioxide which has been produced by our first equation between hydrogen sulfide and oxygen to give us sulfur, which is a yellow deposit, and then we shall also produce water. This is one of the major sources of sulfur. However, it can also cause pollution because the sulfur dioxide is a pollutant and can lead to the production of acid rain, like we shall later see. In Africa here, Nigeria and Uganda's oil do not necessarily have this sulfur, but in some parts of the world, hydrogen sulfide can be obtained from petroleum. So after that, let us move to what we are calling the allotropes of sulfur. We define allotropes, if you remember from our senior 2 work, as the different forms of an element but in the same physical state. So this sulfur has about 5 allotropes, but we shall not put emphasis on all of them. We shall actually put emphasis on only 2, what we are calling the crystalline allotropes of sulfur. Questions can be asking for students to state the crystalline allotropes of sulfur. So those are 2, that's mainly monoclinic sulfur and what we call rhombic sulfur. However, there are other forms of sulfur or allotropes of sulfur, one of them being amorphous. Then there's what we call plastic sulfur, and then there's also a rare form which we call colloidal sulfur. Let us begin by looking at rhombic sulfur, which has also another name which we call alpha sulfur. On the right hand side of our slide we have shown how it appears like. It is octahedral, like you can see in the diagram. Then a few properties about it. It has a melting point of 113 degrees Celsius and a density of around 2.06 grams per cubic centimeter. In some books you will find it written as 2.08, but different books give different figures, either 2.06 or 2.08. That should not be a cause of concern. It is stable at a temperature below 96. We shall later see that if the temperature goes above 96, it changes to another allotrope of sulfur. Then how can we prepare it? If we are interested in preparing this rhombic sulfur, or what we are calling octahedral sulfur, or what we are calling alpha sulfur, it is basically made by dissolving powdered sulfur in carbon disulfide, then filtering the mixture through a dry filter paper, and then the filtrate collected in a beaker. So what we actually do, we get the powdered sulfur, and then we add it to carbon disulfide. Then when we get the carbon, we add it to carbon disulfide. Sulfur, some of it dissolves in the carbon disulfide, some of it remains undissolved. So we shall filter. So the liquid of the mixture of sulfur and the carbon disulfide, which has been able to dissolve, what we do is we get a filter paper and tie it on top of the beaker. We shall be able to demonstrate this when school is open again. And then we punch a few holes, and then we can leave it somewhere, either in a fume cupboard or we can put it on a window, and then leave it to stand for a few hours or a few days. The carbon disulfide, since it is highly volatile, it will escape, and then the sulfur slowly will start forming what we are calling rhombic sulfur, and it is octahedral in shape. You can be able to see that. They are yellow crystals and they are bright in color. Then there is another form of sulfur which we are calling monoclinic sulfur. Here on the right hand side of our slide you can see how it appears like. This one is also known as prismatic sulfur, like you can see its appearance. It is needle shaped, like you can see in the lower picture. It has a melting point of 119 degrees Celsius. Remember, for rhombic it was 113. Its density is 1.98 grams per cubic centimeter. For the other one it was 2.06. Then it exists at a temperature above 96 degrees Celsius. For rhombic sulfur, the temperature was below. So that means there is some kind of transformation if the temperature is either below or above. How do we prepare it? Monoclinic is made by dissolving powdered sulfur, this time around not in carbon disulfide, but rather in what we call methyl benzene. However, the methyl benzene has to be hot. This reaction should not be carried out in the open because methyl benzene is poisonous. So when the two are mixed and then allowed to cool, pale yellow needle-like crystals end up forming. These ones are of monoclinic sulfur, like you can be able to see in this picture here. Then There's what we call the transition temperature. What is transition temperature? This is the temperature at which we change from one form of sulfur to another. And this temperature is 96 degrees Celsius. Rhombic sulfur is stable below 96, like we have already seen, and monoclinic is stable at a temperature above 96. That means if I wanted to convert rhombic into monoclinic, I just increase the temperature above 96, it will transform. And likewise, if I had monoclinic and I want to change it to rhombic, I just reduce the temperature below 96. So that's what it means by transition temperature, the temperature at which one form of sulfur changes into another. So we have been talking about these properties of the different allotropes. So we want to appreciate the differences between these forms of sulfur. Rhombic sulfur is bright yellow, translucent, or they appear as bright yellow translucent crystals. Monoclinic, they are pale yellow, transparent crystals. Rhombic sulfur is octahedral, whereas monoclinic is needle-shaped. We have seen those ones. If you look at the density, this is 2.06, the other one is 1.98. Then the rhombic, like we have already seen, it is stable at a temperature below 96, whereas monoclinic is stable at a temperature above 96. The melting temperatures we have also seen in the properties. Rhombic has a melting temperature of 113 degrees Celsius, whereas monoclinic has a melting temperature of 119 degrees Celsius. It's important for us to know these properties and be able to differentiate, because this question can easily be asked. Then the other forms of sulfur is what we call amorphous sulfur. We have said this is non-crystalline. Notice question can come asking you to state the crystalline forms. That means you can't include amorphous, because for it it's non-crystalline. It's yellow, but that yellow which tends towards white. And how is it formed? By oxidation of hydrogen sulfide by air. If you react hydrogen sulfide with oxygen, we form sulfur and water. That sulfur that we form is amorphous sulfur. Then we also have what we call plastic sulfur. This is formed by boiling sulfur and then quickly pouring it into cold water. Its appearance is kind of yellow, but that which tends towards what? Tends towards brown. Then the properties of sulfur, as we finalize, it is a yellow non-metal, like we have seen everywhere. We have associated sulfur with the yellow color, though these allotropes may have different colors. Like we have seen, some are bright yellow, some have yellow tending towards white, others have a yellow towards brown. And then secondly, it is insoluble in water. It doesn't dissolve in water, which is a polar solvent. It dissolves in non-polar solvents, like we have seen, carbon disulfide, methyl benzene. Those are examples of non-polar solvents. And then lastly but not least, it being a non-metal, it is a poor conductor of heat and electricity, because it lacks the free and mobile electrons. Then, as we finalize, we may need to test our knowledge of what we have learned. For example, can you define what the word allotrope is? And then someone asks you to state or name the crystalline allotropes of sulfur. Can you be able to state them? And then lastly but not least, state the differences between the crystalline allotropes that you have stated. So basically that's what we want to discuss. Shall discuss the chemical properties of sulfur when we upload another video. But for more information, you can check out these websites. Thank you.